Tonight we have Jim O'Connor, research geologist with the Geology, Minerals, Energy, and Geophysics Science Center. He majored in geological science at the University of Washington and earned a MS and a doctorate degree at the University of Arizona. Since 1991, he has worked at the U.S. Geological Survey, intent on improving understanding of the processes and events that shape the remarkable and diverse landscapes of the Pacific Northwest. Tonight, Jim is speaking about the other flood, Ice Age Bonneville Flood on the Snake River. So, Jim, I'm going to turn it over to you. Yeah, right.
That would do it. Okay, so hopefully you're seeing a picture of G.K. Gilbert. So from my perspective, the story of not just the Bonneville flood, but all Ice Age floods in the Pacific Northwest got its first written mention in G.K. Gilbert's field notes of August 16th, 1876. And at that time, Gilbert, who later became one of the icons of North American geology, with a career in the Geological Survey, at that time he was 33 years old, and he was an assistant geologist working for John Wesley Powell on the Powell Survey. And he's exploring some of the basins of the American Southwest. And here he is in far southeastern Idaho, north of the Salt Lake Basin, riding north. And here's what he writes in his notebook. I can see the red rock and beyond it. It surely looks as though there has been a current through. And then riding closer, he reports, the red rock is only one of a number that are here exceptionally bared, in testimony to the stream that has washed them in degrading this pass. Now, here he is describing the outlet of Pluvial Lake Bonneville, an Ice Age lake, and the source of what later became known as the Bonneville Flood. So now we're going to move forward and let's see. And I'm going to step back and provide a little bit of some overall context. And so most of you all know this, but just so that we're all on the same page and on the same time scale, at the peak of the last ice age, 20 to 15,000 years ago, these great continental scale ice sheets centered over Hudson's Bay, the Laurentide ice sheet, and then the mountains of Western Canada, the Cordilleran ice sheet, grew, expanded greatly, and they expanded south, attacking the U.S. from coming south across the Canadian border. And as you know, this for the case of the Missoula Floods, Glacial Lake Missoula was formed by a tongue of that ice coming down and blocking the Clark Fork River. Can you see my cursor? Is that? Yeah. Okay. So a tongue of that ice came down and blocked the Clark Fork River, not too far east of Spokane. And these ice dam lakes were intrinsically unstable. And of course, Glacial Lake Missoula failed, causing the Great Missoula Floods that came across the Channel Scabland and covered the area of Portland where I'm sitting now. But also during this colder and wetter period, the closed basins of the American Southwest started to fill with water. And the two largest lakes were the Lake Lahontan system over western Nevada, and they're not called glacial lakes because they were not ice dam. They were just filling these closed basins, expanding within these closed basins. And then pluvial Lake Bonneville is the Ice Age, or the Pleistocene predecessor of Great Salt Lake. So that's the overall setting. These lakes formed, and many of them breached their dams and caused floods. So what was Gilbert doing? He was searching for an outlet to pluvial Lake Bonneville. He crisscrossed the basin with his assistants in the south end and in the north end, looking for where this lake had escaped. And he knew that it had to have an outlet because of the nature of the shorelines that were formed around this lake. And this is a sketch from his 1876 field notebook, and he draws these two prominent shorelines. The upper one, which he labels in his field books as BB, the Bonneville shoreline, and then the lower one, about 300 feet lower, called the Provo line. And he knew that because these shorelines were strongly developed, that the lake had to have been at one elevation for not just one elevation for a long period of time to form these strong shorelines. And the way that can happen is if the lake had an outlet. What was mystifying to him was the fact that there were two of these strongly formed shorelines. And so he was actually looking for two outlets at different elevations and not quite sure how that story would work out. So he's crisscrossing the perimeter of the expanded lake basin, looking for outlets. And in 1876, as he comes up to Red Rock Pass, the outlet, which is at the far northeastern corner of the overall Lake Bonneville Basin, is where he figures things out. So just to show you what these shorelines look like, here's an aerial view looking down over Salt Lake City, and you can see the upper Bonneville shoreline here and this strongly formed Provo bench. There are weak shorelines below from later when the lake dropped down below the Provo level, but these two strong shorelines are what indicated to Gilbert that there had to be outlets at those elevations. And you can compare that with what the shorelines from Glacial Lake Missoula look like. They're there. This is a view looking west over the town of Missoula, and you can see shorelines when the light is correct or when the snow is correct, but they're subtle and they're relatively faint compared to the Lake Bonneville shorelines. And that's because Glacial Lake Missoula did not have any kind of stable outlet compared to Lake Bonneville. So back to Gilbert. This is a map of the outlet area that appeared in his subsequent masterpiece on Pluvial Lake Bonneville, USGS monograph number 1 from 1890. And as he records in his notebooks, as I said earlier, as I can see red rock and beyond it, it surely looks as though there's been a current through, but it also looks as though the beach line that points nearby was higher than the pass. So this line right here is the Bonneville shoreline up here, and he can follow it up to right about here, where he loses it at the north end of this narrow area called Red Rock Pass. Similarly, on the west side, the bottom of the pass, indicated by the blue tint, is the level of the Provo shoreline. So here's the Bonneville shoreline, here's the Provo shoreline. And so it's clear that this present outlet geometry is what controlled the lake level at the elevation when it etched the Provo shoreline. But it also becomes evident what happened here as he traces the shoreline here and he loses it at this area of this alluvial fan that's coming in from the east, from the mountains to the east. It's called built out by Marsh Creek. And so you can imagine what the situation was prior when the upper shoreline was cut, that this fan extended all the way across here and impinged against the mountains to the west. And that was the low point of the divide between the closed Salt Lake or Bonneville Basin and what to the north is the Columbia Basin, and specifically that of the Snake River. So instead of looking for two outlets, what he has decided is, well, there was really only one outlet, and it was here all the time. It's just that the outlet elevation has changed because when the lake started pouring over at the Provo level, it started cutting through this unconsolidated material of the alluvial fan until it reached hard rock 300 feet lower, 100 meters lower, which governed the final outlet elevation, the Provo level. So so Gilbert sketches the scene from a spot right about here viewing south. And here's the scene. Here's his donkey, which he named Ways and Means. I think a play on the federal budget process. And here is he's standing on the Marsh Creek fan. This is Red Rock Pass here, and it's looking south into Cache Valley and the Bonneville Basin. And the level of the Provo, the Bonneville level was up here somewhere at the level of the crest of the fan, and the Provo level is down where the railroad is at the bottom of the valley. From the air, it looks like this. Gilbert and his Ways and Means were down here sketching. Here's the valley bottom as it appeared in the late 1980s. And this is the Provo level. This is Cache Valley and to the south, which is part of the larger Bonneville Lake Basin. So here's a story of what happened as Gilbert told it in 1890. And the story hasn't really been improved upon much at all. So I'm just going to read what he wrote. The fact that the Bonneville water discharged at first over a barrier of alluvium instead of solid rock had much to do with the subsequent history of the lake. Uncemented alluvium is easily and rapidly torn up and removed, and as soon as a current began to flow across the divide, it must have commenced the excavation of a channel. As the channel increased, the volume of the escaping water became greater, and this increase of volume reacted on the power of erosion. In a short term, a mighty river was formed, and the lowering of the lake surface resulted. For a time, the outpouring was a veritable debacle, and it could not have assumed the phase of an ordinary river commensurate with the inflow of the lake until the alluvial barrier was completely demolished and the resistance of the limestone reef was called into play. So that's essentially the story as we still understand it. what's kind of interesting is that there were intervening interpretations that were different, but Gilbert's original account is pretty much the current scientific consensus of what happened. I want to point out a couple things about this quote. He basically is describing a positive feedback process. It's once the erosion started, you have more water coming through, which is going to increase erosion at even a higher rate. And of course, that happened until the channel lowered to the point where it hit the much harder limestone at the bottom. He talks about it as a mighty river, and he describes the outpouring as a debacle, but he never uses the word flood, and I've always wondered about that. So, again, here's Gilbert's map. The lake level dropped from the Bonneville level down to the Provo level, dropped 300 feet. That resulted in the lake going from about an area of a volume of about 10,000 cubic kilometers to 5,000 cubic kilometers. So about half of the lake's volume emptied out through here. More recent modeling has attempted to model that process. And I'm not going to spend a lot of time with facts and figures. I think the qualitative story is interesting enough, but there's a few things that are kind of interesting. This black line is essentially a hydrograph describing the discharge with time. So this is the peak discharge, or this is discharge on this axis, and this is time in days on the x-axis. And as Gilbert described, that overflow at first was low, but then it was a positive feedback process, and then it exponentially increased until it hit the solid rock, and then it decreased more slowly as the lake funneled out through this narrow constriction. So this is kind of the nature of the outflow. And one thing that's interesting about the Bonneville flood is, and I will compare it crudely to the Missoula floods here. So this is the same picture as the last one. And here's essentially a hydrograph for the Missoula flood near Spokane. I don't really have it. It's not in terms of discharge. It's just in terms of water height. But what's interesting here is this little square represents about 100 hours of time in the x-axis direction. This whole hydrograph is essentially over in 100 hours. So the deal with the Bonneville flood was that while its peak discharge was probably only a 10th or a 20th of that of the largest Missoula flood, its volume was twice that of the Missoula flood, and its duration was much, much longer. So it has a different character to it than the Missoula floods. And I think that shows up in what the deposits in the landscape looks like. So when did the Bonneville flood occur? That's been a good question. It's a good question for the Missoula floods. We keep struggling with the exact timing of the Missoula floods. For the Bonneville flood, the best information comes from our understanding of Lake Bonneville itself. We don't have a lot of dates on deposits from the Bonneville flood, but we do have a lot of dates from lake sediments as this lake was evolving with time. So here's the last ice age, starting about 30,000 years ago. It gets colder and wetter, and the lake levels increasing. This is the elevation of the lake surface. goes up and fits and starts until it reaches that Bonneville shoreline, controlled by that alluvial fan, the Marsh Creek alluvial fan at Red Rock Pass. It overtops and it drops down to the Provo level. This is the Bonneville Flood right here. It remains at the Provo level, carving the other shoreline for a while before evaporation finally exceeds the influx into the basin and the lake drops down to near the modern Great Salt Lake elevation by 12 or 13,000 years ago. But the dates for the flood itself are converging on about 18,000 calendar years ago, plus or minus a couple hundred. So in terms of the timing of the Bonneville flood, where it was pretty close to 18,000 years ago, which was near the beginning of the phase of Missoula, of the last glacial phase of Missoula floods. So one thing that's interesting about the Bonneville flood was that it was lost and forgotten for several decades. Gilbert describes it in his field notes. He describes the Bonneville River and the debacle in his 1890 monograph, but then nobody else talks about the Bonneville flood and its downstream effects. And what's especially curious about that is that there were two very major reports done in the Snake River Plain in the early part of the 1900s. The first one was by Israel Cook Russell in 1902, Geology and Water Resources of the Snake River Plain. He actually takes a picture of the flood boulders, describes them as water-worn masses of basalt, but he does not link it to the overflow of pluvial Lake Bonneville. And what's really curious about this was that, I showed you that map of Gilbert and all of his assistants and his assistants crisscrossing the Bonneville Basin looking for an outlet. Russell was his main assistant on all of that work. So it's not like Russell didn't know about Lake Bonneville and the overflow. He just didn't put it together there. Similarly, another study in the 1930s by Harold Stearns, who's done a lot of work in Oregon and Washington in his career as well, detailed study on the geology, and again, is also partly focused on groundwater in the Snake River Plain. He too took photos of these boulder deposits left by the flood, but did not link them to the overflow. It really wasn't until the early 1960s when Harold Hal Maldy, as everybody knew him by, linked up the overflow of pluvial Lake Bonneville at Red Rock Pass to these boulder deposits and the spectacular scabland terrain, as it turns out, of the Snake River Plain. And he published this in the professional paper in 1968, a study of the colossal features of erosion deposition produced along the Snake River by the sudden overflow of Lake Bonneville. So here, the Bonneville River finally graduates to become the Bonneville Flood. Hal Maldy was an excellent photographer, and he also had kind of an interesting sense of humor. He took lots of pictures of these boulder bars in the late 50s and early 60s. He actually gave the gravel deposits a geological formation name. He called it the melon gravel. And he wrote that he was inspired to that name by a whimsical billboard that advertised one patch of boulders as petrified watermelons. We, referring to Maldy and Powers in the earlier short paper, applied to them the descriptive name melon gravel. So one side story is to name, if you're going to name a geological formation, you have to name it after a place. And he did. There's a place called Melon Valley in the Snake River Plain, in the central Snake River Plain, a little bit west of Twin Falls. And I can't remember if Hal told me this or if I just thought it was a great story and I made it up in my mind. But for some reason, I think Hal had that valley named Melon Valley officially so that he could name the melon gravel after it, all because of that sign. Well, he took me to that sign in 1987. So in the late 80s, I was a PhD student in Arizona, working under Vic Baker, and for some reason, I was interested in megafloods. And I thought a good project would be to look at the Bonneville Flood and try to quantify some of the qualitative observations that Hal Malde had made. And Hal Malde was exceptionally supportive. He had just retired earlier that year in 1987, but he took me out for several days to show me places that he thought would be good to work at. Well, of course, he took me to the petrified watermelons sign that was still there in 1987, and it was actually still there a couple years ago, last time I went through there. And that's me. I was freshly married at the time. I thought, well, this is kind of a good idea. I will take one home to my mother-in-law. I'm not really sure how that went over. I'm pretty sure she doesn't have that watermelon anymore, but I did. I ended up doing my PhD dissertation on the Bonneville Flood. It was published in 1993, but this work was just one of many that looked at Bonneville Flood features once Malde had put the flood back into the picture. And from all that work, we could trace the flood downstream and its features. So here's Red Rock Pass at the north end of Lake Bonneville. The flood flowed north out of here, down Marsh Creek, then down the Portneuf River, entering the Snake River Plain near Pocatello, and then followed the Snake River Plain, bifurcating in a couple places to the west, and then north through Hell's Canyon to Lewiston, and then continued down the Snake River. And you can trace Bonneville flood features down to about here, right where the S is in the Snake, where Lower Granite Dam is. And from here downstream, they're buried or have been removed by Missoula flood deposits or erosion. Hal Malde's work was mainly in this central Snake River Plain area. So this is a map view. In profile, here's what the flood looked like. This is the modern Snake River profile, and the heavy dark line here from Red Rock Pass to the Snake Clearwater confluence at Lewiston. And then this gray line here is the profile of the flood itself at maximum stage from the Lake Bonneville surface down here. You can see that in some ways the profile follows the interesting profile of the Snake River. You know, it's steep over the steep section of the Snake River in the Twin Falls and Shoshone Falls area, and it's also steep in the steep Hell's Canyon reach. But there's also some interesting blips in the profile. Like behind this tight constriction here at Swan Falls, the water was hydraulically ponded, just like the Missoula Floods were upstream of the Columbia River Gorge. It shot through here and then was ponded again at the constriction at the head of the Hells Canyon Reach near Farewell Bend, near Ontario, Idaho. So these steep and shallow reaches, these constrictions and wide spots, really controlled the nature of the flood effects, just like they did for the Missoula floods, but they were much easier to quantify for the Bonneville flood because there was only one flood and it had a much steadier flow, had much longer duration than the very short, flashy Missoula floods, which make the hydraulics exceptionally complicated. So we're going to look at some of these reaches here. The short, steep reach near Twin Falls is famous for another reason. This is where Evel Knievel tried to jump over the Snake River Canyon back in the 1970s. I was a kid back then, but I can remember that failed attempt. He didn't really get very far, actually, before he crashed down in the river below. But here in this section, the waterfall section, Twin Falls, Pillar Falls, Shoshone Falls, Cauldron Lynn, the canyon's really narrow and the water actually filled up and spilled out and took a couple different paths. And here's what it looks like on the ground. Well, not on the ground. This is from the air. These steep reaches had these spectacular erosion complexes. This looks like the channeled scabland of eastern Washington with these cataracts and dry falls on this scoured and fluted basalt, the multiple channels. Here's the interstate over here for scale. This is a Bruce Bjornstad photo. And if he is listening tonight, he maybe should say something at the end about his beautiful new book that has just been released on the Ice Age floods. So this is classic scabland, which actually factors into the Missoula flood debate because, as many of you know, Bretz really had a hard time convincing the masses of the fact that there were these huge glacial floods. And one of his chief nemesis was Richard Foster Flint, a pretty renowned geologist at Yale. And so he had some cred, so to speak, and he kept pushing back on this on Bretz's flood hypothesis. Well, one of his lines of evidence was this scabland near Twin Falls. So in 1938, this is Richard Foster Flint's argument against Bretz, that these scabland features and these bars were carved by leisurely streams with normal discharge, grading and then degrading. And then he pulls out the scabland of the Snake River Plain. He writes, at Shoshone Falls, just east of the city of Twin Falls, Idaho, on the Snake River Plains, the Snake River has incised a canyon more than 500 feet deep. A broad shelf on the south wall, about 100 feet below the rim, consists of scabland with small anastomosing channels, isolated buttes, and shallow rock basins. The thin, vertically jointed flows yielded to the hydraulic force of Snake River as similar flows in the Columbia Plateau yielded to the hydraulic force of proglacial streams. Yet I am not aware that unusual floods have been held to have affected the upper Snake River. So maybe if Gilbert had used the word flood instead of river, the story of the channeled scablands might have evolved differently. So, okay, so that steep reach was right here in the Shoshone Falls area. Much of the classic scabland terrain of the floods is right here. As you go downstream, where the flood slopes were lesser, they started depositing and including some of these spectacular boulder bars that Hal Maldy took me to in the late 80s and described and beautifully photographed. This is a Hal Maldy photograph of one of these boulder bars downstream of Twin Falls. Here's a photograph photograph of slackwater or an eddy bar, finer deposits left by the Bonneville Flood. Here's some more of these deposits. They look an awful lot like the Missoula Flood deposits because they're basically the same type of rock. It's basalt that's been put through the mill by the flood. As you go further downstream, you get to the Swan Falls constriction, and the water jets out through there and deposits these immense bars in this reach between Swan Falls and Farewell Bend. Again, Hal Maldy took some beautiful photographs of some of these bars. This is south of Boise. So here's Swan Falls right here, south of Boise, and this is a birds of prey national refuge area, and it's a beautiful place to go to if you ever have time. You're near Boise. It's a half hour or so off the interstate if you're just driving through the Snake River Plain. It's well worth a visit. Here's another view. Here's the Swan Falls Dam right here. We're looking upstream. Here's a big point bar with a road going up. This is the bedload of the Bonneville Flood. And for scale, is the daughter of the recipient of the petrified watermelon. More photos of these. This is just an incredible place to go to. This photo is from just a couple years ago. In the backwater areas, just like for the Missoula floods, are Sockwire deposits. Here's Sockwire deposits up the Boise River Valley. They look very similar to the Missoula flood rhythmites, except for there aren't these multiple beds like there are from Missoula floods. They're just a massive sequence of laminated silts and sand. So we're going to move downstream from the backflooded Boise River Valley down into Hell's Canyon. Here's a photo taken in 1965 before the dams went in. Here's a big flood bar right here. This is called Big Bar. The crest of it sits above. I can't remember if it's which dam, which pool this is in, but the crest of the bar sits above the pool still. This is a little further downstream in the undammed wild and scenic reach. This is called Pine Bar. So here's the Snake River heading north through Hell's Canyon. I think this is called Suicide Bend right here. You can see these terraces here. These are really flood bars that are lapped up against the hill slope. You can see a nice flood trim line up here. This is all eroded colluvium and slope material. You can see this big point bar complex right here with these full-size ponderosa pines for scale. So even in Hell's Canyon, which is narrow and confined, and there's not a lot of flood deposits in places where there's just a little bit of room in the valley bottom, there are these pretty spectacular flood deposits. You don't get the classic scabland in Hell's Canyon because you just don't have that flat line basalt like you do in the Snake River Plain or on the Columbia Plateau. And then downstream, near Lewiston, this is Tammany Bar. This is another place that's easy to get to. You can see these coarse foreset bedded gravel bars with all sorts of Hell's Canyon lithologies. This is Bonneville Flood deposits that were this big bar that was growing from right to left here. And it's here capped by some 20 Missoula Flood rhythmites that came back flooding up the Snake River. And this is why, as you go further downstream, and these deposits get thicker and thicker, and that you lose evidence of the Bonneville Flood, as I said, downstream of it's about Lower Granite Dam on the Snake River. So there's lots more work that could be done on the Bonneville Flood. The work that I did now more than 30, really 30 years ago. God, it's hard to say that, but it was 30 years ago. It was okay for the time, but the hydrodynamic modeling capabilities are so much better now. And because this flood was steady and long lasting, the modeling is going to be much more accurate than it is for the Missoula floods. So this is a study that that really should happen. But if we could do new hydrodynamic modeling, we could make the movie of the Bonneville Flood. But also importantly, we could start really getting a better idea of what are some of the thresholds and processes associated with megaflood processes in a much more tractable situation than for most megafloods. And that would be a valuable exercise. We can start asking questions about how do these cataracts and dry waterfalls and alcoves form, and think a little bit more in a more sophisticated manner about sediment transport and how sediment transport processes relate to the sedimentology and stratigraphy that we see in these bars. And then there are also some specific questions regarding the Bonneville Flood that are still that still could use some work. Was this narrow canyon that Evel Knievel tried to jump over, was that carved entirely by the Bonneville Flood? I think it's possible that it was. That prior to the flood, the main channel was what I've labeled here as Eden Channel. We know that situation happened up here in the Massacre Rocks area, where the pre-flood river channel was at the north end of the flooded domain. And during the flood, a cataract eroded back up along the south end and ultimately became the main river course after the flood. What about other floods in the Snake River Plain? There were ice dam lakes in the mountains of southern Idaho. We know that some of them released floods that came down the Wood River and the Big Lost River. How much of an effect did those floods have on the Snake River through here? And then what were the effects of the Bonneville Flood in carving Hell's Canyon? Hell's Canyon is a recently new route of the Snake River. It's been in existence probably for 2 or 3 million years. So it was there prior to the Bonneville Flood. But how much did the Bonneville Flood serve to deepen and widen the canyon of Hell's Canyon? And then we can see that Bonneville Flood deposits are underneath at least some Missoula Flood deposits up here at Lewiston. but did the Bonneville flood predate all the Missoula floods? It's kind of a close call. From dating that we've done elsewhere in the Channel of Scabland, we know that the earliest Missoula floods, the last glacial episode, were about 18,000 to 18,500 years ago. So it's kind of within, it's about the same time that we're thinking the Bonneville flood occurred. So one last slide. How that kind of summarizes the Bonneville flood and also compares it with Missoula floods. So the Bonneville flood was twice as big as the largest Missoula flood in terms of the volume of water. But the Bonneville flood, as I said earlier, had a peak discharge that was probably about 1/20th that of the largest Missoula flood. And that's a difference between a 2,000-foot lake bursting an ice dam compared to a 300-foot spillover of the Bonneville flood. It just took a lot longer for the water for the Pluvial Lake Bonneville to go through that constriction at Red Rock Pass than it did for Glacial Lake Missoula to empty once that ice dam was taken out. So Bonneville flood lasted for months compared to days in Missoula floods. Bonneville flood was a singular flood. It was a one-time thing. Once that Marsh Creek alluvial fan was eroded away, there was no real mechanism to generate another unstable lake volume. Not like the Missoula floods, where the ice dam was relentless and coming back down and reblocking the Clark Fork and forming Glacial Lake Missoula. We now think there were more than 100 Missoula floods compared to the one Bonneville flood. But one similarity that's very important to me is both floods in the Sockwater areas produced great hops growing soils. So I think that is my last slide. And if folks have questions, I'd be happy to make stuff up to answer them. Okay, I see one question there. How do we know that Bonneville flood didn't create Shoshone Falls? Well, we don't know that. I suspect that it did create Shoshone Falls and Twin Falls, that they're similar to cataracts that formed in other places along the flood route, but those cataracts still host the Snake River. Shoshone Falls, I believe Shoshone Falls is there in part because it's a different rock type that is emerged out of the bottom of the canyon there, a more silicic, harder rock type that provides a little bit more resistant than basalt. But my suspicion is that those falls, those cataracts, were formed during the flood, and then they've probably been modified by post-flood flows, but probably not to a large extent compared to what the flood had left there at its end. Did the dam burst originally just from water pressure? Well, it was I don't really so the dam was this broad alluvial fan. There was definitely water pressure against that fan, and there's evidence for water percolating through the fan, but the pressure itself wouldn't be enough to push the material out of the way and then trigger a release. It would take the flowing water that was picking up material to actually start incising into the start incising into the fan and then dropping the lake level. Okay, so next question I see is, I'm still unclear as to the source of the Bonneville floodwater itself. It's clear in the Missoula Floods that the Clark Fork River Basin was the source. So the source of the water for the Bonneville Flood is really the same source as the water that's presently in Great Salt Lake. It's the Wasatch Mountains, it's the Bear River drainage, it's the Sevier River to the south. But during, presently, the level of Great Salt Lake is the result of the balance of that water coming in with the amount that evaporates each year. And so if you have a period of wet years, the lake comes up, as it did in the 80s and drowned the airport, and the Utah State Legislature passed a law prohibiting it to rise any further. I'm not sure how much good that did. But then you have dry years and the lake level comes down. You have centuries and millennia of wet years, the lake level just keeps coming up and coming up and coming up. And that was the source of the water, that water coming up for 10 or 15,000 years of a surplus hydrologic budget, essentially, until it hit that threshold elevation at the Marsh Creek fan. So, and then the same question for the breaching of the lower Provo limestone dam. So that dam, that level did not breach. The lake was at that level for probably several hundred years or 1,000 years, because you had a surplus hydrologic budget. So for during that period at the end of the last ice age, the predecessor to Great Salt Lake was not a closed basin, it was part of the Snake River Basin. And there's some fish passage evidence that suggests that fish in the Snake River Basin came up, fish in the Salt Lake Basin came up from the Snake River during that time period. But as we came out of the ice age and things got drier, pretty soon the amount of evaporation, even from that greatly reduced Provo Lake area, exceeded what was coming in from the Wasatches. And then the lake started shrinking down towards its Great Salt Lake level. And it's been down there about that level for the last 10,000 years. So it did not, there was no flood from the Provo level. The lake could come back up to that level, and it will at some point if things go well. But it's been and if the Marsh Creek fan builds out again in the interim, you could set the circumstance up again for another Bonneville flood. Hopefully that answers the question. Let's see. How were the rock carried as far as Lewiston with different in the rock? So yeah, that's a good question. So what the question I think is getting at is because the flood is depositing in these flat reaches, how do rocks get all the way down to Lewiston? And I think the answer is that they don't. The deposits that you see in Lewiston were probably derived from Hell's Canyon, almost all of them. The deposits that you see downstream from Swan Falls, almost all of those rocks came from that Swan Falls constriction itself. It's kind of one of the hallmarks of megaflood deposits is that the sources of the materials are usually quite local from the next constriction upstream. It's when you have normal rivers operating, you get far traveled rocks because the really hard rocks from the Tetons, the quartzites and stuff, they'll make it all the way down to Portland over thousands of years and thousands of small annual floods, bringing them down step by step. They don't wear away like the basalts do. So that's a good question, and it brings up a good point. So is a current Salt Lake is just a Provo level that has evaporated. That's correct. All right. Is the Bonneville flood traceable in the Tushy area? It hasn't been yet. There's just been so much erosion by the Missoula floods or come in from the Cheney-Palouse tract that a lot of stuff is eroded away or it's buried by Missoula floods. And then you also have the issues that's talking about is flood deposits are so commonly locally derived that once you get into the domain of the Missoula floods, it'd be really hard to tell a Bonneville flood deposit from a Missoula flood deposit. At Lower Granite Dam, you still can. You see these Hell's Canyon lithologies, these green metamorphic rocks there that don't come from the channeled scabbard. They can only come from Hell's Canyon. But because the Bonneville flood was so much smaller than the Missoula floods, that there's been nothing in the Columbia River Gorge, in the Woola Gap area, in the Lower Snake River area, that anybody has been able to attribute to the Bonneville flood, as opposed to being from the larger, more recent Missoula floods, to my understanding.
Okay, do we have a couple more questions there?
Maybe. Yeah, see, I don't see any in the chat, but
no.
Anybody wants to speak up, that works too.
Yes, I'd like to know what the Owyhee Canyon River, did it play a part in the Bonneville floods?
That's a good question. It certainly was back flooded. In the lower part was back flooded. I can't say that I spent a lot of time in the Owyhee River, but much further upstream. So I'm going to guess that the situation is similar to the Boise River and the Weiser River and some of the others, where you see, like for the Missoula floods, you see these great hot producing flood silts deposited back up these valleys in these back flooded areas. And I would guess that would be the same situation for the Owyhee, but I can't say that I have actually seen them. All right, so let's see. I'll be driving from Seattle to Moab, and so if you have time, if you're driving through the Snake River Plain, get off the interstate if you can. Take Old Highway 30. You'll see that stinker gas station sign. Especially if you're driving east, you'll see the important side of the sign. The other side of the sign is actually an advertisement for stinker gas. That's a petrified watermelon sign, I should say. Excuse me. And if you really have time, head south to that birds of prey wilderness area. You can drive down to the bottom of the canyon and walk amongst the huge bedload there. It's pretty mind-blowing, and it's really a really cool spot, and there's all sorts of birds of prey there too. The Red Rock Pass itself is not on Interstate 15. It's just a few miles to the east of it, and there's an interpretive sign there, and it's a nice, quiet, and very interesting place. So I could spend 10 days doing that drive. Did the Bonneville Flood reach the Columbia River? Well, it certainly did. But as I said earlier, there's not really any evidence of it. There might be evidence offshore where at about 18,000 years ago, the drill cores have detected a big pulse of freshwater plankton or something like that, some sort of biologic thing that indicates freshwater. And I think the Lake Bonneville is a good candidate for the source of that because it was a large freshwater lake. It was probably much more biologically productive than Glacial Lake Missoula was. How would you compare public awareness of the Bonneville floods in Utah and Idaho to public awareness of the Missoula floods in Idaho, Washington, and Oregon? E.g., residents of Portland's Alameda Ridge know about the Missoula floods. I think it's probably similar. Folks, especially along the Snake River Plain, they're living amongst the flood bars and the scabland. They know about the flood. There's guidebooks that have been written. There's interpretive signs like there are for the Missoula floods. The city of Pocatello sits on top of a boulder bar, so anyone who has to replace a water line or anything like that, they know about the Bonneville flood. So I think there is some. I think it's pretty similar level of awareness in the Salt Lake Basin. They've lived with the ups and downs of Great Salt Lake for decades now, and I think a lot of people there know how that recent history ties into the longer term history and the Ice Age history as well, because the benches that's what they're called, the Provo Shoreline and the Bonneville benches are really prominent features in the landscape there. The hospitals, those benches were big flat places that were easy to develop. The hospitals and universities are on those benches. One interesting thing about that too is a lot of the Bonneville flood deposits are being mined out. Not the Bonneville flood deposits, the Lake Bonneville deposits are being mined out, and there's been an initiative there to protect them as geological resources, which I think is interesting. We really haven't had anything like that to my knowledge associated with the Missoula Floods. You know, are there gravel bars for the Missoula Floods that we should protect from development? And that's been the hot issue in the rapidly developing Salt Lake area. I see Bruce left me a nice note. I think, Bruce, maybe you should say a word about your book, if that's appropriate.
Do you know the name of his book that you were referencing, Jim?
I do, and I'm going to have to pull up. I want to make sure I get it right. It was published by Springer Nature, and it is called Ice Age Floods of the Pacific Northwest. And Bruce, tell me if I'm doing something wrong here. Oh, it's already on there. I don't want to steal Bruce's thunder, but I think a lot of people who are on this would be interested.
I think that they would really enjoy. Bruce has been doing just exceptional work with drone shots, etc. So Ice Age Floodscapes of the Pacific Northwest sounds like it would be just a fabulous book documenting and just showing the beauty of a lot of that area. He really does a nice job on that. Let's see if we have a couple more questions in the chat room. Oh, Bruce says, thanks for the plug. You're welcome, Bruce. You do great work. Thank you. I think that is it. So thank you so very much. Go back to a gallery view here. And we want to thank everyone for joining us tonight. Really appreciate the turnout. Jim, excellent talk. Thank you so very, very much. Yes,
well, thanks for listening to my story.
Oh, yeah. Great research. So just a reminder, those of you who are members of the Ice Age Floods Institute or maybe have been members, please make sure your membership is paid up. And if you are not a member, please consider joining us, because this is how we're able to bring you talks, etc. Thank you again for joining us. Thank you again, Jim. Certainly appreciate it. Good night, everyone.